Okay, let's get started. So last time I thought I would do the proof of a particular theorem about vector-valued differentiation of vector-valued functions, but I think I'm gonna, I'll get to that later. I'm gonna go backwards. I've been doing things a little bit out of order compared to Rudin, so today I'm gonna go sort of follow Rudin's order. Okay, so for the topics. But first, let me just remind us what differentiability. Just so let's recall again what differentiable. What does it mean by f differentiable at a point, right? And the definition I'd like you to keep in mind is this one, that that being differentiable in x means that your function can be expressed as the tangent line, right? Your function can be expressed as the linearization, right? Plus this thing, this error term that vanishes, right? Where the limit of u of t is 0 as t approaches x. Okay. Okay. So this thing, right? The linearization plus error. Okay. And one thing that we used in so for example, if f prime x is positive, then if f prime x is positive, one thing we used was basically that maybe I just say it like this: observe if f prime is positive, then we can actually choose since u of t goes to 0, right, as t goes to x, then we can choose. We can find a neighborhood of x in which the size of u of t is smaller than 1/2 f prime of x. Right. Right. So, so the picture is you have some function. Here's x. Here is the linearization. Right. And f prime of x is some positive. Right. We've got some positive slope here, and we can choose a neighborhood of x in which u of t is smaller than 1/2 f prime. Okay. Okay. So just think. Let me rewrite this. So in that neighborhood, f of t minus the tangent line of course equals, the error, right? Of course, right? And if I put absolute values on it, right, what I see is that the difference between the function in that neighborhood, the difference between the function and the tangent line is controlled by 1/2 f prime, 1/2, this m, all right, there's, the slope times absolute value of t minus x. Right? Okay. So what does that mean? That means that the difference between your function, so we can find, so suppose this is our point f of x, and then we have some slope, we have some tangent line. tangent line with slope f prime x, right? And if we look at the difference between this and this, we see that it's smaller than 1/2 this times this, right? Well, this 1/2 this times this basically is saying that is saying that if you take a line of half the slope, so if you take the line with slope 1/2 f prime x, and you take the slope with 3/2 f prime x, right? Then what it's saying is that the function minus the line is trapped between here and here, right? The function minus the line is trapped between here and here, right? So in other words, you can find a neighborhood. You can find a neighborhood so that the function is trapped inside this I don't know what you want to call it, this bow tie like thing. Okay, so this is how you want to think about differentiability, right? That your function can be made as close to the line as possible in this sense, right? That you can trap it in this sort of bow tie like thing. Okay, and that's what we used when we were talking about the proof of the critical point theorem. This is the thing we used in the proof of the critical point theorem. Yeah. Plum.
Yeah, I just want to restate so for any function that has f of x is greater than 0.
F prime x.
That has derivative greater than 0.
Yeah.
This for any point in the function that has derivative greater than 0, then the function value is the function value is bounded by that bow tie in terms of right?
Yeah. So what we're saying is that your function is it actually doesn't have to be greater than 0. Well, but I think it's useful. It's useful. So yeah. So if the function, if the slope is greater than 0, then you can take the slope plus half and the slope plus minus half of you can take 1/2 the slope and 3/2 the slope, and you can trap the function. That you can find a neighborhood in which the function is trapped between those two lines, between this upper line. Well, on the right it's upper, below on the left it's lower, and this other line. Okay. So right, this is a consequence of the fact that this thing goes to 0. Right? Because this thing goes to 0, we can make this thing smaller than 1/2 f prime, and so the error is just you can have at most this much error, and you can have at most this much error, right? So your function, it has to be that close to the tangent line. Okay. So now let's go to this thing that Rudin calls the continuity of the derivative. Okay. And he starts out by pointing out that that derivatives don't have to be continuous. So he gives this example, and he says, well, look, if you look at the function f of x equals x squared sine 1/x when x is non-zero, and 0 when x equals to 0. What this function looks like is, right, you've got the x squared and you've got the negative x squared, right? And you multiply sine 1/x by x squared. And so basically, you see, as x goes to 0, this 1/x goes to infinity, right? And so what you have is some function that what you have is you're multiplying the sine function but it's a sine function that increases, that speeds up as you get closer to 0. But you're multiplying it by x squared, so it looks something like this, right? So it's kind of slow on the outside, but then as you get closer, it's the frequency speeds up. Okay. And so the function is going up and down and up and down and up and down, right? So the slopes, as you're heading towards 0, it's still going to have this oscillation, right? But so the slopes don't converge, right? So this function, the derivative, is discontinuous. At 0. Right. What happens is that the slope at 0 is just 0. Okay. The slope at 0 is just 0, but as you approach 0, the derivative oscillates back and forth, and so the limit is not 0. The limit doesn't exist as you head towards 0, and you can do the calculation using the chain rule and see how that works out. Okay. So this shows that that derivatives don't have to be continuous. Okay, you can have a derivative and it's discontinuous. But there is something nice, which is kind of a intermediate value property of derivatives. So derivatives always have to satisfy an intermediate value property. So let me make sure I get this down right. So we have a function on AB, and f is differentiable on AB. Okay. And I should have said this earlier, but when Rudin says differentiable on a closed interval, he means that you're for the left endpoints, he means you're differentiable from the right-hand side, right? That the limit, differentiable f prime at a is going to be the limit of f of a plus h minus f of a over h as h approaches 0 from the positive side, right? So he's not going to differentiability from the right at a just means differentiable from the right-hand side. Is that okay? Right. So because the function is not even defined on the left-hand side, right? For functions in the interior, you have your normal, you have your normal both-sided derivative. But on the left, for this point, he means one-sided derivative, and for the endpoints, he means one-sided derivatives. Okay. So. So you have a function, it's differentiable on AB, and you assume, let's just, for convenience, let's assume that the derivative at A is smaller than the derivative at B. Okay, so then for any intermediate value, for any value lambda between f prime A and f prime b, you're guaranteed a point. Inside AB where the derivative equals that value. Okay. So whenever you have two points x and y, and you have one slope here, and you have another slope here, you're guaranteed, to attain all intermediate slopes. Okay, you're guaranteed to attain every single intermediate slope. Okay, so and the way he does this is by saying, well, look, consider the function g of x defined as f minus I'll use t because he uses t. That's what I have in my notes. G of t equals f of t minus lambda t. It doesn't matter. Okay, so right? So let's look at this thing. You take your function and you subtract off, this line of slope. You subtract off the line of slope lambda, and of course it suffices to show that g prime is 0 somewhere. Right? Because that would mean that f prime is lambda. Right? Okay. Okay. So right. So this is a this function, but this g is of course differentiable, also differentiable on AB, right? Because f is, and certainly the line is differentiable there, right? Okay, so all we have to do is show that okay, so all we have to do is show that that g attains a max or a min, right? Because if g attains a max or a min, then inside, then it must have a slope of 0 there. Okay? So so think. If we look at g prime at a, right? G prime at a is going to be f prime at a minus lambda. G prime at b is going to be f prime at b minus lambda. Right? Right. But lambda is bigger than f prime of a, so this thing is small, this thing is negative, and lambda is smaller than f prime of b, so this is positive. Right? Okay. So now we're gonna so if we're thinking about g, we know that the derivative is negative there, right? The derivative is negative there. The derivative is negative here, so the slope of the tangent line is negative, right? The slope of the tangent line is negative here, right? And again, we can trap it between two lines between two lines that are really close to the tangent line, right? And so since we can trap it so close to the tangent line that we know that the function must be decreasing in a small neighborhood. Okay, so that's the idea, right? So choose a neighborhood a plus delta in which u is smaller than 1/2 g prime a. Right? Then we know that at most this function has a slope. The function is trapped beneath something that has negative slope. Right? So then g of t is smaller than the line of smaller than g of alpha plus what should I write here? Plus the thing that has plus g prime alpha t minus a plus 1/2 g prime alpha t minus a. Right. Sorry, I'm kind of maybe this isn't clear, but I hope the idea is clear, right? That what you do is the slope is g prime alpha. The slope of the tangent line is g prime alpha, and then you choose your neighborhood so that you're trapped under the line. You're trapped under the line of g prime alpha plus 1/2 absolute value of g prime alpha, right? And so that ensures that your function is decreasing because you're trapped under a decreasing function. Right. I'm sorry. That ensures that you've got values that are smaller than this point here, right? So anyway, the point is that this is not the minimum. Right. So. Right. In other words, right, we've got g of t is smaller than g of a plus 1/2 g prime alpha to minus alpha. Right. And this is negative. This is negative. That's negative, right? And so g at alpha is not a minimum. Okay, and then you do the same thing on the other side. You say, well, look over here, the slope is positive, right? And so you know that since you can trap the function close enough to the tangent line, you know that the function can't be a minimum here, right? So similarly for the other side, similarly, g of b is not a minimum, right? And so you know that a minimum, there has to be a minimum between a and b, and that's where the derivative is 0. So g prime c equals 0 for some c between a and b. Right. So this is for all t in a plus delta. Does that make sense? This is actually right. Yeah. Right. You trap the function. You trap the function underneath the tangent line, plus the maximum error, right? Trap the tangent line under this plus the maximum error, and this thing is negative. So when you add on half of it, when you add on half of the absolute value of it, you get half of the negative value, right? And so what you get is you see that this thing is smaller than something with negative slope, right? The function is smaller than something with negative slope, and so can't have a maximum there, can't have a minimum there. Sorry. Okay. Does that make sense? Make sense? Okay. Make sense? Yes. Okay. Okay. So the continuity of derivatives is done. Okay. Let's get on to the other stuff. Okay. So the other thing we're going to do, which is kind of fun, is the so getting back to consequences of mean value theorems. The other thing we're going to do is L'Hopital's rule. So Rudin has a pretty cool statement of L'Hopital's rule, which is actually a little different from what you might have learned in calculus. So let's write it like this. So you have 2 points A and B, which are between, these are points on the extended real line. So they could be negative infinity and positive infinity. Okay. And so suppose that F and G are differentiable on the integral AB, which could be the whole line, and G prime is never 0, okay, on that interval. Okay, and suppose that that the limit of the quotient of the derivatives is some value as x approaches A. Okay, and A again can be could be finite or infinite. So A could be positive or negative infinity, or any number in between. So if, so here's the one that you probably are familiar with. If the limit of f of x as x approaches A equals the limit of g of x as x approaches A, and they're both 0, then the limit of the quotients is A. Right? That's the one that you're familiar with. But there's a slightly stronger version. So what you're probably going to think I'm going to write here is that if I'll write the same thing with infinity here. Right? If the limit of both of these guys is infinity, then the limit is A also. Right? That's what you learn in calculus. But actually, you can do a little bit better than that. All you need is that the bottom guy is infinity. Okay. If the limit of the bottom guy is plus or minus infinity, then the limit will also converge to A. The limit of the quotient will converge to A. Okay. 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 So yeah. So I kind of forgotten about that, but let's do the proof. So just for simplicity, let's do the case. We'll do the case where A and A are finite. Okay. So okay. So we want to show that that this thing is A. Okay. So okay. So we want to show that the limit of the quotients is actually A as x approaches little a. In other words, we want to show that that we can find a neighborhood. We can find a neighborhood of A in which this thing is, So, in other words, given any epsilon greater than 0, there exists a neighborhood of A in which, a punctured neighborhood of A in which f of x over g of x minus A is smaller than epsilon. Right? That's of course what a limit means. Okay, so what we're going to do is say, well, look, we know the limit of the quotients. The limit of the quotients is A. So we know there is a neighborhood in which the limit of the quotients of the derivatives is A. So we know there's a neighborhood in which these guys are close to A, right? So we know there exists a neighborhood of A in which this thing, this thing minus a is smaller than epsilon over 2. Right? Okay, so here's a. We know that in this punctured neighborhood, all of these quotients of the derivatives are are close to a. Okay, so now we pull out the now pick any 2 points x and y where x is less than y in the interval, say a plus delta. Okay, so choose 2 points x and y, and we're going to use the extended, the generalized mean value theorem. Okay, so by the generalized mean value theorem, we know that f of y minus f of x over g of y minus g of x equals f prime c over g prime c, right? For some c between x and y, right? That's what the generalized mean value theorem says, right? That that if you look at the quotient of the instantaneous velocities, you get the, quotient of the average velocities, you get the quotient of the instantaneous velocities. Right? Okay, so, but we know that this thing, right, this thing is in the punctured neighborhood, right? So this thing lies inside the punctured lies inside the epsilon over 2 neighborhood of A. Right? This thing is within epsilon over 2 of A. Right? Okay, so that tells us that whenever we look at this sort of quotient, it lies inside there. Right? It's close to A. Okay. Now, is that okay? Okay. So now let x tend to A from the right-hand side. Okay. As x tends to A from the right-hand side, both f and g go to 0. Right. So we get that f of y over g of y, lies inside of the closure of this neighborhood. Okay. So as you take this limit, this thing might go to the limit point. Okay. Might tend towards some limit point, but it'll stay inside the closure. That's why we took the epsilon over 2. Okay. So which is within epsilon. In any case, it's within epsilon of A. Okay. So so that does it, right? We wanted to find a neighborhood. We wanted to find a neighborhood of A in which the ratio was within epsilon of A, and we found it. Right? We found it. Okay. I guess I only did it from the right-hand side, but you can then do it from the left-hand side as well. Okay. So that's how L'Hopital's rule falls out of the mean value theorem. Any questions? Okay.
Wait, Prof, can you try to draw the closure again? I suppose I on the left-hand side.
Oh, as x goes to A plus this part?
Yeah. Can you draw that neighborhood with closure?
Yeah, sure. So let's see. So let's see. So you know that that this thing, whenever we take x, y inside here, right? Then this ratio lies inside the epsilon over 2 neighborhood of A, right? So I don't know if this is going to help, but here's A, and here's the epsilon neighborhood, and here's the epsilon over 2 neighborhood. Right? Here's the epsilon over 2 neighborhood. And you know that this ratio guy here, right, always lies inside of here. Okay. Then when you take the limit, there's a possibility that that limit will end up actually at the epsilon over 2, right? Okay. When you take the limit, but that's okay. What we really wanted was that for that thing to stay inside of for that thing to stay inside the epsilon neighborhood. So we're okay. Okay. So it's basically the same sort of argument as saying that, well, look, you could have, 1 over n is always greater than 0, right? But when you take the limit as n goes to infinity, you see what happens, right? You can end up at 0, right? So it's the same sort of thing could happen, but it doesn't matter because we've chosen it to stay inside the epsilon neighborhood. Yeah. Yeah. Okay. So I'm wondering if I should do the more complicated version. Do you guys want to see? Do you guys want to see this part? Yes. Okay. Good. Okay. So. Okay. So. Okay. So same sort of thing. Same sort of thing. So again, choose x and y inside that neighborhood A equals delta, right? And then we look at, just as before, we look at this thing. Okay, and this thing is going to lie in, right? Same argument as before. This thing is going to equal, some quotient of the derivatives, and so it lies inside the epsilon over 2 neighborhood of A, right? So this thing is going to be trapped between A minus epsilon over 2 and A plus epsilon over 2. Okay, we're just saying the same thing as before, right? That this thing lies inside inside here. Okay, but we're gonna mess with it a little bit differently this time. So okay, so multiply by multiply by gx minus gy over gx. Okay. So what do we get? We get A minus epsilon over 2 times gx minus gy over gx is smaller than f of x minus f of y, gy minus gx. Wait a second, is that right? I think I probably should have written things backwards. Does it matter? Sorry, this should be backwards. X, Y, X, Y, X, Y.
Why didn't you keep the order and then switch the order of multiplication?
Yeah, it doesn't matter. It's the same thing, right?
Yeah, I was thinking about just removing the denominator too.
Yeah, that's what we're gonna do. Yeah. So we have this thing times, of course, gy minus gx minus gy over gx And then a plus epsilon over 2 gx minus gy over gx. Okay, right. Let me rewrite this. This is a minus epsilon over 2, 1 minus gy over gx. Right. Here, of course, these things cancel, and I get yeah, that's good. F of x minus f of y over gx. One minus gy over gx. Right, and then I'm going to add on. I'm going to add on, let me write this as okay, and then I'm just going to add on this term throughout. Okay, so I get a minus epsilon over 2, 1 minus gy over gx plus fy over gx less than or equal to f of x over g of x. This 1 minus gy over g of x plus fy over g of x. Okay, and then okay, so this is true. This is true for any xy inside the neighborhood, right? And so now we let x go to a, right? So let x approach a from the right hand side, right? You see what happens, right? As x goes to a, g of x goes to infinity, right? So this thing turns into a 1, right? This vanishes, right? This thing turns into 1, and this thing vanishes, of course, right? And so what we get is that the limit is right? We get fx g of x lies inside of the epsilon over 2 neighborhood of a. Okay, so that's it. Okay, let me see if I can finish up with the vector value theorem that I wanted to finish up with last time. So here it is. The useful so it's Rudin points out in his book that you can have a mean value theorem for vector valued functions, and he gives some examples. So I'll let you read those. Hopefully you've read those examples. But there is a theorem that kind of acts as a substitute for the mean value theorem. It's not as strong, but gives you something along the same lines. So here it is. You have some vector value function, and as usual, it's continuous on the closure and differentiable on the interior. Okay, so then you're guaranteed a point in the interior where the size of f of b minus f of a over b minus a is controlled by f prime at that point. So this isn't as powerful as the mean value theorem, right? The mean value theorem says that there's some point where the you'd like it'd be cool if you could get something like where the derivative actually equals the difference of the function divided by the change, right? But that doesn't work. Okay, but you can get this sort of like size constraint, right? So for example, if you knew that your derivative were 0, right, then of course then your function wouldn't move at all, this sort of thing. Okay, so the proof is to use the mean value theorem. Use the mean value theorem on a different function. So the function you're going to consider is phi defined as the difference between the endpoints dotted against the function. Okay, so this thing here is just a one variable. Phi, as you see, it goes from R to R. Right, here it goes from the interval AB to R. Right, because you're taking the dot product here, so you just get a scalar out of it. Right. Okay. And it's differentiable and continuous because of the conditions. Okay. So we apply it and we say, okay, so by mean value theorem, we know that there exists some point C in B such that phi of B minus phi of A over B minus A equals phi prime at C. Right? But what does that mean? Well, phi of B minus phi of A is just f of B minus f of A dotted against f of B minus the same thing dotted against f of A, right? So I can distribute out this term and get f of B minus f of A, right? This is just a constant, right? This is a constant vector, right? We get this thing dotted against f of B, this thing dotted against f of A. We take the difference and we can factor out this thing and get that, right? Okay. So that we get that over B minus A equals f prime of C. Well, f prime of C is going to be just this constant vector dotted against, phi prime of C is going to be just this constant vector dotted against f prime of C, right? Because this is constant. You're differentiating when you differentiate this, the derivative is just going to fall on this part. Right? It's a constant. Okay, so what does that give us? These two things are equal, right? And so if we take the magnitudes of both sides, right? Let's take the magnitudes of both sides. I'm sorry. Yeah. So this thing here is the magnitude squared, right? What's this? This is the magnitude squared of this. Right? Vector dotted against itself is the magnitude squared, right? That thing is equal to this. Okay, but we can use the Cauchy-Schwarz inequality and say that this thing, right? That thing is less than or equal to the product of the magnitudes. Right. I hope you remember the Cauchy-Schwarz inequality that says that the magnitude of the dot product is bounded by the product of the magnitudes of the two vectors, right? So here we have the dot product, right? And the dot product is controlled in size by the product of the magnitudes, right? And then we're done, right? Because we just cancel off, this thing from both sides, and we get that f of b minus f of a over b minus a is smaller than that. Okay, as suspected, I went 3 minutes over. Okay, but that's it. Okay. So that is that's basically all the stuff. You see what we did. We in this chapter we defined what differentiability meant, and then the main thing was to get the generalized mean value theorem, and then from the generalized mean value theorem, all these other results follow, like Taylor's Taylor's theorem, L'Hopital's rule, this sort of vector valued thing, et cetera, et cetera. So that's yeah. The derivative controls the behavior of the function, and it's the generalized mean value theorem. It's the mean value theorems that allow you to see how the derivative controls the function. So next time we're going backwards into chapter 3. So we'll go back to sequences in series. Okay, we'll do sequences in series, and then we'll end the course with chapter 7, which is sequences in series of functions. Okay, see you all. Have a nice break.